Let's look at some op-amp buffers with various open loop transfer functions. So in Ltspice, I've made up some various op-amp models, and over here we can see their equations. The first one is just the open loop gain times the difference of the inputs of the op-amp. And see, there's no S parameter or anything, so it's just DC and it's just static. Then we have an integrator type configuration. We have a low pass type configuration with one pole, and then we have a second order and it has two poles. I keep adding these omega knots so that the gain bandwidths all line up. You can see that I programmed it here in Ltspice, and we have model 1 conforms to model 1 over here, 2, 2, 3, 3. So let's look at the Bode plot, and we can see for the green there is our open loop gain, and it's constant versus frequency. That's that model. Then model 2, and again I've added a term here just to make sure that everything lines up, and we can see that it's an integrator, right? The red and the blue are overlapping, so you can't tell, right? But it's really, we have an integrator function times the difference. Then over here we have a first order low pass filter times the difference, and that's the red. And the second order, we can see that it starts off, comes down, and then you see another break. We see for the second order the phase goes from 0 to 180. For the first order low pass filter, that's red, you see a phase of minus 90, and it's being overwritten by the second order. It's on top, so it comes there. And then the phase for the integrator is minus 90 the whole time. Right, and you can see it here, and then it gets overwritten by the other models. Now, let's see what happens when we use various models for a buffer. And I've just drawn this a slightly different way to make it look a little more like the signal flow diagram, where we have the sum, there's our sum, and then we have the basic op-amp model, right, which is fed back in through a resistor network, which happens to be 1 for a buffer, right, because what happens is R1 goes to infinity and R2 goes to 0, which would give us a 1. And so really the V out equals the op-amp model times V in minus V out times beta times the op-amp model, which will be determined later. So our transfer function, V out over V in, is the op-amp model divided by 1 plus beta times the op-amp model, which really, when beta equals 1, because it's just a buffer. Now, when will this circuit act like a buffer? And again, this is configured with R2 is 0 and R1 is infinite, right? So we have our op-amp model. So this is a transfer function when we're using model 1. So we have the open loop gain divided by 1 plus beta times the open loop gain, beta equals 1, and we have this function. When will this act like a buffer? Well, if the open loop gain is much, much greater than 1, then this transfer function will go to 1. And what's much, much greater than? About 100 times bigger. Then for model 2, we have the open loop gain times an omega naught divided by S. So this is our integrator function. We multiply it through, and then we get something that now is time dependent, and it looks like a low pass filter. And so if S equals j omega, really if the open loop gain portion is greater, much, much greater than the frequency, then we're going to get 1, which is a buffer. Now for the single pole where we have an omega naught, we just multiply everything through, and now we have an open loop gains constant here, s plus omega naught, and this has to be much greater than this term so that it can cancel. So, but now we have a complex thing, so I'm just going to say the magnitude of this just has to be much, much greater than the magnitude of that, and then it'll collapse to 1. We have a second order. We just put in our second order transfer function for the OPAMP, and we'll get this, where we have a second order here plus a constant. Now, to say when will it behave like a buffer, well, when this is a lot bigger than this whole part, right, when the magnitudes are greater, then it'll collapse to 1. So, as you can see, in the first model, it acts like a buffer no matter what the frequency. Here, at some point, when the frequency gets close to the open loop gain, it's going to stop acting like it. When the magnitude of the frequency plus the pole is getting close to this, it's going to stop, right? And then the same with the second order. Now, what about ringing? Right? Which models can ring? Which can be underdamped? Well, this has no memory, no S term. V out is just going to be equal V in instantaneously, right? It transfers whatever it is instantaneously. So there's no time dependence, it's static, it can't ring. And here we have a first order. First orders can't ring. In order to ring, you have to have a second order with complex poles. So the first three can't ring. Now, the fourth, well, let's manipulate this a little bit. And we have a second order. We have 1 times s squared omega naught plus omega 1 times s plus a constant. So it could be underdamped. How would we know? Well, let's just calculate the poles, which is really just what's going on here. If this term is bigger than that term, right, we're going to have plus or minus a complex pole, which is just summarized here. Now, it could be overdamped, it could be critically damped, but if this is going on, we could have a situation where when we put in a step response, it's going to go above the step and then settle down to the step value. So I modeled this in Ltspice, and basically I have V in, which is the input, and when I put comma, the output of whatever it is I'm doing, that's really this minus that. And so it's a really quick way to do a buffer, right? I could put, if I wanted a beta, I could put 0.5 times that, and then I would actually have, a gain of 2. Then I have the Laplace transform part. So really, V in minus VB1 is the long way to do it. Using the comma makes this minus that, which is a shorthand. Ltspice file you can download. And so look, the green is model 1, and it's always acting like a buffer. Models 2 and 3, right, are actually matching each other perfectly, and the phase goes down to minus 90 because they're first order, right? So around 100K is when it's still operating. And then interestingly enough, for the values I chose, we have a second order, but notice that it goes out a little bit farther before it starts to go down. And of course the slope is twice. This is minus 40 dB. And that's in fact because this has some complex poles and is actually acting like a Butterworth filter, which we'll get into later. But this spot, right, the minus 3 dB point is actually occurring at minus 90, where here it's minus 3 dB spot is operating at minus 45. If there were two repeated poles, this would be at minus 6 dB at minus 90. But that's going to be on the final. So we're going to go over that later. Now, I wanted to investigate some other things, and basically, there's the universal OPAMP model, and they have models 1, 2, 3A, and 3B. And then there's also Ltspice models for the 1006, the 1037, and the 1630. And this is just the open loop gain. And we can see that the 1006 part, it's high, it breaks, so there's one pole, then there's another, and it keeps going. And so we've got 360 degrees worth of phase. So just what? Divide that by 90, and that should give us the order of the filter. The 1630, it's following it almost the same, but the phase is doing some, let's say, interesting things. And then the 1037 has some, again, some interesting things. And in fact, the 1037 will oscillate on you if you're not really careful. No, this isn't really on going to be on the exam, but these are real world transfer functions of the op amps. And something to note is up to 100K, where the phase is below minus 90, well, they're all kind of acting like these models over here, where right, where as long as the open loop gain is high enough and I've got a phase of minus 90, these are pretty much going to work, right? And so the open loop gain divided by S, is a pretty good approximation. Even if you want one pole, still it's a pretty, so one pole is pretty good for all of these, almost, about to 100 kilohertz. Um, really have to be careful with this 1037, but that's a discussion for another day.